first speaker this morning is going to tell us about this title. Kind of amazes me, the idea that you could be on a pathway toward designer Hamiltonians, one atom at a time. But Craig will explain all of that. Craig Fennie of Cornell.
Thank you, David. Yes, the title is supposed to conjure up lots of exciting imagery and images and get you to think about the possibility of actually doing this, right? My pleasure to be here. What I wanted to do today is to tell you a little bit about that title and this challenge of designer Hamiltonians within the context of materials design and complex oxides. I then want to, this is a very broad challenge, something that I'm incredibly interested by and consumed with, is that first thing there. But we'll try to narrow that down a little bit and give you some ideas on how one can go about designing materials to be realizations of Hamiltonians, a sort of design strategy. And then we'll narrow it down a little bit more and give you some examples of where, unfortunately, not necessarily Hamiltonians, but classical microscopic models, starting with a model, a microscopic model, how these things interact with each other, we can end up with a material realization of that within the context of these magnetoelectric multi-fluid materials. And I'll probably end there, perhaps one intriguing slide. The last bullet point of can we actually use these same ideas to control the metal insulator transitions. So what is this big challenge that I'm talking about here? What it has to do with Feynman's last blackboard. I found this image recently. It's much nicer than my handwriting, but still perhaps not necessarily clear. So I'm assuming this is a pointer. Yeah, good. Okay, so we have lots of things written here. This one right here is know how to solve every problem that has been solved. I've had peers for 3 graduate courses and not time for one. I'm sure they can tell you that probably isn't the case with me. It's probably not something I'm going to ever be able to do. Learn data onsets. Again, not time will probably stop us right there. That's probably not the case. But this one up here is perhaps, this is the one that intrigues me. It says, what I cannot create, I do not understand. I've heard this phrase in several different contexts. One that I cannot, what I cannot compute, I do not understand. What I cannot calculate, I do not understand. But I never realized the original quote was, what I cannot create, I do not understand. It sounds a bit strange, right? Particularly with our usual approach to creating new materials and discovering new phenomena, right? Let's take a little bit of a detour, and I love cartoons to really illustrate points. What is our usual approach to discovering new materials and new phenomena is best described by these 2 people here. This scientist here is trying to develop this brand new product that's going to revolutionize the company. It was a total flop. They were going after an insect repellent, but however, it's a killer acne drug. Materials, new phenomena are usually discovered completely by accident. One of more related to my field is this. It was interesting to see in the New York Times a few years ago this happy accident chemist produced a new blue. Master Brahmanian, a friend of mine, a solid-state chemist at Oregon State, discovered this new blue pigment. Blue pigments, I'm told, are expensive and usually rather poisonous. This one is none of those. It's an oxide material. It's quite benign. In fact, he is now just not only made blue, he can make every color in the rainbow out of this material. It is actually, he's starting companies. It's revolutionizing the paint industry. Mass, as some of you may know, has worked a lot on sort of correlated electron phenomena, superconductors, blah, 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 multiferroics. In fact, he was going after, and he was showing a couple of multiferroic, this yttrium manganese oxide. And in fact, doped with this indium, but that's not really important. The doping was supposed to make this the world's best multiferroic. It was terrible in terms of its magnetoelectric properties, but they discovered this Again, things are discovered by accident that change, that lead us to new places. And so really, the usual approach that we're seeing is that new materials are discovered. Properties that we wouldn't expect them to have are measured, and we try to work out what they mean and to try to understand them at a very deep level. I see this challenge that we have is, can we start with some Hamiltonian? And here is just an example. It's quite simple, and it doesn't really matter what I have written here. The point is, it's just a Hamiltonian. Can we start with this Hamiltonian that we've solved in some way and we can qualitatively describe some macroscopic phenomena with? How do we go from that to a real material? And that is the question that I have been obsessed with. And we've, in the last session, we heard these words already: Materials Genome Initiative. These are a lot of buzzwords: materials by design, blah, blah, blah. But as some of you know, and perhaps all of you know, the White House a few years ago had this idea that we have this genome initiative where we sequence everything and we learn all about biology this way. Can we do the same with materials? Can we compute every material and every structure and with every chemical species, and somehow this huge amount of data is going to teach us everything we want to know about materials, and all the discoveries will magically pop out. Within this context, though, materials design and discovery mean different things to different people. One, I like to break these up into very extreme views. One is, if I'm just given ABX, what crystal structure could be synthesized? Or perhaps a more practical question, what is simply the equilibrium ground state? Very interesting question, but more related to the context of this idea of designer Hamiltonians is another way of thinking about materials design, is that what specific elements, for example ABX, and what arrangements in space give me some property or functionality that I'm interested in. And as long as one can find a meta-stable structure, the question then turns around was not necessarily, the question turns around to being not what material do I really need, but how do I stabilize this metastable structure. Put this in a little different context. We're up here. We're starting with some effective microscopic theory. How do we find material realization? The first step, and we'll show some examples of this later today, is to come up with some materials candidates. How do we go from that step of the theory to the material candidates? There's a lot in there. And the examples that I'm going to show you, it really relied on physical and chemical intuition. How do we construct at the level of atoms and arranging atoms in space? How do we find those motifs that allow the interactions of our microscopic theory? How do we then build up those motifs into an extended structure? If we have no chemical intuition about the system, or physical intuition about the system, how can we generate that? We heard a talk yesterday by Jacqueline, great talk, of a way of doing that. We could perhaps data mine known structures, or we could perhaps compute unknown structures, or chemistries in unknown structures, and mine those as well. So data mining, these inference maps, all of these computational techniques are great ways of developing chemical and chemical intuition where none currently exists. But once we have these realizations, we can then turn to our first principle quantum mechanical techniques to see if these material candidates really are realizations of this of microscopic theory. And the final step I've left here often question marks, because in some cases you hit a home run and you find that structure. You find that material that is your realization. Most often, in my experience, that structure is not stable or would have been found already by some chemist making things. It's usually metastable, and the question then does turn, how do I stabilize that metastable structure? More often than not, finding this last step is a little bit more tricky than finding this last material realization that can actually be made in the lab is a little bit more tricky than one can imagine. And in my mind, a lot of times is not necessarily the end game here, right? That design rules, if we could theoretically get at a set of chemically intuitive design rules to then take to our chemist friend and work with them to find this material and realize it in the lab, is really the goal of our theory. And just a little play on words here, the design rules are good enough. Imagine deriving good enough kind of moral rules from first principles. That's a very powerful, simple set of rules that help us find material realizations. All right. Materials that I'm interested in, I was told this was a very broad audience, and I'm assuming, and I'm realizing it's probably not as broad as I once thought, but I'm interested in rocks, right? Complex oxides, or rocks. One of the most interesting set of complex oxides are perovskites. Here's the actual mineral, calcium titanium O3. Perovskites, silicates, the most abundant mineral in the lower mantle. Rocks tend to look more like this, or at least the insulating rocks that we play with.
Those are pretty rocks.
Yeah, they are pretty rocks. All clear though, so still no electrons in the problem. That's for another talk. But here is perhaps in my mind the simplest example of a complex oxide. The perovskites, which I mentioned on the previous slide, it's simple in the sense that the prototypical structure seen here is relatively simple. It's a cube. Can't get much simpler than a cube on a lattice. There's only 5 atoms in this prototypical structure. It's an ABO3 compound. A sits in the corner of the cube. B sits in the center of this oxygen octahedra. The octahedra are corner shared, and there's a 3-dimensional network of these octahedra. They're complex because small changes in the chemistry lead to vastly different properties. The perovskites alone display just about every known physical property that exists in nature. Adding to the challenge and the opportunity in these materials is that just about the entire periodic table in some way fits into the structure. So these color codes are supposed to suggest that just all the transition metals, these blue things here, can fit on the B site. All of the alkali metals, all the alkaline earths, the athanites can all fit on the A site. You can have multiple cations on the A site, multiple cations on the B site. You have an enormous number of possible compounds that can exist in this one structure. If you think about the various size differences of these primarily ionic cations and anions, you can question how does this one structure accommodate all this chemical diversity. It's that this idea that we have this cubic perovskite is a bit naive. Very few perovskites are actually forming a cubic structure. Most of them, in order to accommodate all of these different cations, distort. The octahedra distort in various patterns. 2 common patterns are that these octahedras rotate. The 2 most common ones here is one pattern known as the orthorhombic perovskite structure. Here is a rhombohedral distortion, of the octahedra. And it's because of these rotations that we can accommodate all of these different cations. And the reason why I'm harping on these very subtle and a lot of times small structural distortions is because, believe it or not, these very subtle distortions control the properties of these materials. Here I'm just showing you 2 phase diagrams of 2 examples. I could show you for just about every transition metal oxide a diagram like this. This is a rare earth manganite, this is a rare earth nickelate from the bottom. What you're seeing here is temperature versus some parameter, which I'll mention in just a bit. The dots refer to different compounds, from lanthanum all the way down to holmium in this case. These are all 3+ cations. Again, these are all 3+ cations. These are isovalent substitutions. We are not adding or taking away electrons, simply changing the size of the cation on the A site. And what I'm showing you over here is the manganese-oxygen bond angle for this top graph. So that is the angle between the atom here, let's say the manganese atom here, the oxygen, the manganese. If this was a cubic structure, this would be 180 degrees. As we make the cation in the A site smaller, this rotation increases. As you can see here, as we make the cation smaller, the rotation angle decreases more, sorry, the deviation from 180 degrees increases more and more. The rotations become larger. What I'm showing you down here, it's plotting versus tolerance factor. Just know what way of plotting that. The tolerance factor is a geometric descriptor. Imagine that we have this cubic perovskite structure, and just imagine that you could pack these as hard spheres. The ideal packing of hard spheres would lead to a tolerance factor of 1, but if the A site was much smaller, this tolerance factor would be less than 1. Chemically, that means that the A site is, its bonds are very unsatisfied. The crystal structure will want to distort in order to accommodate the chemistry of its A site bonding environments. And that's what we're showing here. As the A site gets smaller, the tolerance factor gets smaller, and the system distorts more and more. These very subtle rotations completely control the correlated valence states in these materials. We can completely tune between different magnetic states in this rare magnet case, completely tune from, this is the lanthanum nickelate as a metallic phase all the way into an insulating phase just by changing the rotation angle, the rotation patterns, et cetera, et cetera. These small distortions are key to understanding and controlling the properties of these materials. Recent advances in synthesis allow people to make these materials one atomic layer at a time. Techniques known as molecular beam epitaxy or laser PLD or off-axis sputtering allow these beautiful materials to be made in structures that don't exist in equilibrium. You can imagine making superlattices such as the one shown here. Here's some high-res TEMs of various structures. This one here, the center one is perhaps 10 years ago or so, really ignited this field of complex oxide interface and interface physics in complex oxides, because this is an example of taking two materials that are bulk, lanthanum titanate and strontium titanate, which are both insulators. And by making this digital superlattice, by making at the interface between these two insulators, this is a mod insulator, this is a band insulator, two-dimensional electron gas emerged. This is a great example of what one can do using these techniques. And so more is definitely different in the field of complex oxides. There's just an enormous number of possibilities of things to do with these materials. And as a theorist interested in material design and predicting new phenomena and discovering new phenomena, that is a challenge. How do we get a handle of all of this enormous, and I hate using this word here because, but I will, complexity of the problem. And again, cartoons, I love cartoons, and I hope you like joking in the morning. But this has really led to a typical experimentalist view of theory predictions. Here's two experimentalists sitting around the fire and say, yes, it's a wonderful discovery, theory discovery, but whatever you do, don't touch it. Times are changing, right? There are new theoretical methods, new theoretical techniques. I'm not going to talk about them. It's not really relevant for the points that I want to make here. But also new ways to think about materials design. That is what I want to talk about. I view these experimental, huge leaps in our experimental capabilities of making and characterizing these materials as an opportunity. An opportunity to control, again, this word is popping up everywhere, structural complexity of this problem. We can put atoms where we want to, right? By putting atoms where we want, we can control the interplay of these various microscopic degrees of freedom, the charge, the spin, the orbital degrees of freedom, and produce and control the macroscopic, observed macroscopic phenomena. What I'm going to show you today is how we can manipulate the structure, put the atoms where we want to control the, again, sorry, this is a little out of, but anyway, control the interplay of microscopic degrees of freedom. But what really I'm going to do is to start with the Hamiltonian that looks something like this. We'll describe what this is when we get there. But again, we have this Hamiltonian. We're going to place atoms. We're going to find those structural motifs that allow us to control the interactions, that's these J's and D's here, to produce new phenomena that doesn't exist. Right. Sorry. Getting a little too excited. And in fact, we're going to design structures in such a way that these parameters are controllable with an electric field. So we have a Hamiltonian. We need to find a realization of that Hamiltonian. We're going to, this realization, we're going to construct in such a way, atom by atom, such that these parameters of our Hamiltonian are controllable with an electric field. All right. The more specific challenge. Can I design a general materials platform for which an electric field couples naturally to different correlated ground states? When I need this, for example, can I take an electric field and turn a ferromagnet into an antiferromagnet, or vice versa? Since most complex oxides are antiferromagnetic to begin with, it would be really cool if we could take an electric field and take those spins that are pointing like this, make them all point in the same direction. We also do the same thing and control metal unstable transition. Can we design a general platform where both of these things are realizable? An approach that I love to think about to really produce this coupling, these strong couplings to external fields, is based on an idea that's pervasive in materials physics: phase competition. Here's 3 different phase diagrams. Again, it's not too important what they are. This one is a magnetite. This one is PZT. It's lead, zirconium, titanium 03. And this one is a solid solution of terbium iron 2 and dysprosium iron 2, known as terphenol D. This one displays a colossal magnetoresistive response. This material here is displays what we call a colossal electromechanical response. It's the best known piezoelectric material that exists. And this one is our best known colossal magnetostricted material. The underlying, the universality of all of these things is that where these large responses occur are right in the vicinity of these vertical phase boundaries shown here. So the idea is that one tunes to a phase boundary, and in the vicinity of these phase boundaries we have these large responses. So can we tune to a boundary and take advantage of these various phases that are competing to produce sort of large and colossal responses? Very schematically, what's going to be key to everything that I'm thinking about in order to take this electric field and have it couple to the underlying degrees of freedom is the idea that underneath, in this material that we're creating is a ferroelectric. In fact, the starting point is to start with a material that is a paraelectric and decides a way of controlling this paraelectric to ferroelectric transition. And we've seen examples before. In this PZT, that's exactly what's going on. We're using chemistry to do this. We don't want to introduce any disorder. We don't want to just make random alloys. We want to find new control parameters in order to tune to phase boundaries. But then, we want to add to the problem other degrees of freedom. So imagine that we start with a material that is paraelectric and has property 1, and we can define some control parameter that if we were able to tune this parameter, we'd be able to tune to a material that's ferroelectric and has a different property. And so we have to come up with ways of coupling all of these different phenomenological properties, these phenomenological order parameters, if you will.
Question.
Yes?
Is property 1 and property 2 are completely unrelated to the biological products?
Exactly. So here's an example in the next slide, or 2 different examples. Property 1, imagine this phase, it's in example 1, and this is what I'll talk mostly about today. Property 1 could be paraelectric and antiferromagnetic. Like most complex oxides with magnetic degrees of freedom are antiferromagnetic and paraelectric. Let's start with one of those and come up with a way of tuning to a phase that is ferroelectric and ferromagnetic. In another example, you can imagine taking a paraelectric metal, and somehow, this is I don't want to get too bogged down bog down on now. We can come back to it at the end if there's time, because this is what I'm really, really excited about today. Imagine paraelectric metal and coming up with a way of tuning to a phase that's ferroelectric. In other words, it has to be insulated. So now you're coupling a paraelectric metallic phase to a ferroelectric insulated phase. You've coupled the metal insulated transition to a system that has a polarization and one that doesn't. You're coupling all of these different degrees of freedom. There's a chance, and it could be a way of controlling that metal insulated transition within
This is a mod insulator.
field. What's that?
This is a mod insulator.
It would be a mod insulator, yeah. Right, so actually all of these systems are mod insulators that we're talking about. In this first example, and this is where we spent a lot of working on, these are mod insulators that are very far into the mod insulating phase. These are very good these are very good insulators. Very far from the transition. Whereas these bottom ones, you can imagine being much, much closer to the regime where the correlations and everything becomes much more interesting and much harder to describe. Yeah.
I just want a really basic question.
Sure.
You have a lot of finesse with this, but how would you define a mod insulator to an experimentalist?
There's at least 5 people in the room who could do a better job of that
No,
than
I
me.
want to hear you because you're doing a great job.
Okay. So how I would describe it is a very naive view.
Okay.
My naive view is that, and there's just caveats and blah, blah, blah. Let's forget all about that. Very basically, to an experimentalist, first shot, a mod insulator is a material that is insulating, yet band theory would predict it to be a metal.
Yeah, okay, I have the same problem. It's very unsatisfying. Okay,
It's
fine.
very unsatisfying. There's, particularly when you get closer and closer to this transition, I have no idea what's really going on.
And with all your experience, can you predict what mod insulators can be doped?
This is
These are hard questions like this. I'm sorry.
No. This is so. In the past 6 years, I've worked on this problem a lot, and that part. Sorry.
No, I'm saying we like to talk.
Oh, okay. That's good to hear in the middle because I always get sort of chewed out by silence. I did do my PhD at Rutgers, where that was not that never happened.
I was like, we're so quiet and shy at Rutgers.
Yeah, I mean, your first slide you could spend half your talk on. And I was at those talks. It wasn't mine. But, this is where I'm heading. That's the sort of questions that I want to learn more and more about, and one of the things that I'm trying to reach out to the broader community to start discussion. How do we do this? How do we think about it? How can we do it? This one is a little less interesting from that perspective, but much greater.
Can we press you on that, Craig?
Yeah,
Did you ask me the question, can you predict which ones you can and cannot?
I can.
No.
The best that I would ever, but I have not thought hard about this problem yet, but my guess is that I could not.
Most of them don't dope, right? You just can't dope mod insulators, most of them.
Yeah,
Unfortunately.
unfortunately. Yeah. That's the question. But the idea, not to get too distracted, just to follow up on this a little
I
bit.
kept about getting distracted in the middle of your talk. It's
What?
good, it's good.
Okay. Is that a fundamental, again, this more and more that we're learning about mod insulators is that correlations are incredibly important, but so is the structure. And the structure has been almost ignored today. If we could focus on that problem, try to manipulate the structure to get closer and closer to this boundary between the metal and the insulator, then these sort of questions of can we dope them, can we actually control these transitions, and so forth. I'm hoping in a very naive way that it becomes easier to deal with and easier to understand.
That structure is very important.
Structure is a very important part of it, and we almost, as a community, have ignored it today.
Maybe this is maybe more of a rhetorical point. You don't have to respond to it because I don't want to keep you talking. But and also may reflect the fact that I've sort of been out of strong correlations for 10 years or so. But it still strikes me, and correct me if I'm wrong, I don't know of any examples of real experimental mod insulators where there's not a broken symmetry. So then you can also, once you form the insulating state, you can also see that there's the electron counting works out. So that in fact it's both it's an insulator also. Once the symmetry is broken, it's an insulator also by the electron counting. But I'm willing to be proven wrong by that. Jim?
So the real issue is whether you're forcing yourself to discuss this at t equals 0 or not.
Yeah.
If
Yeah, I'm talking about T equals 0 there, right?
Yeah, so you take the PI phase of B203 was always said to be the famous example of a real mod insulator because then I wasn't magnetic and it still was an insulator. But I think conceptually you can't take the PI phase of B203 all the way to T equals 0 because what do you do with the entropy? I mean, just as a simple-minded way to put it, then you got a bunch of magnetic moments and if you're not going to order them, something's got to happen. And so then you're into issues like spin liquids and topological order and stuff like that.
Right.
So I think that's the deep philosophical question, or not philosophical question, but the deep theoretical issue is exactly that. And that's, I think, the issue that Bob Laughlin has been raising in his arguments with Phil Anderson, probably. Exactly that, whether you have to be a finite T or not, and if you have to be T equals 0, you can't have it there, is that a real phase of matter? I mean, those are the kinds of issues under discussion.
And then we should let Craig get back to the flow of his talk.
Yeah, I'm done. Yeah, I don't know how to follow that. But it's like, first we're starting about consciousness, and then I'm like, wow, I gotta get up and now talk after we just talked about consciousness. All right. Yeah, good. So, yeah, these properties, one property two, are distinct from paraelectric and ferroelectric. Going right back in line with the question you asked. Let's talk a little bit about this example. And this is, again, in the context of, I think, what I was asked to talk about in terms of multiferroics. For those, we heard a good talk yesterday from Fennie about multiferroics. I won't say too much more except to realize, or again, just introduce some definitions. Multiferroics, the material that has a spontaneous electrical polarization and a spontaneous magnetization. The goal in this entire field of multiferroics is, to get back just a step, these are inherently multifunctional in the sense that an electric field couples, in the sense that they respond in a useful way to more than one external perturbation, such as an electric field coupled naturally to a polarization, the magnetization couples naturally to the magnetization. Again, this is a homogeneous single-phase material. But really the goal in this field is to increase functionality by taking advantage of a magnetoelectric effect. And that is what I'm calling any cross-coupling between these two very different order parameters. And in the context of my goal, and perhaps an incredibly fundamental and technologically relevant question is, can I take an electric field and control magnetism? Can I turn it on and off? Can I switch the magnetization 180 degrees? Which is a challenge that still has not yet been made. And the way that I'm going to go about this is by designing into the material a strong coupling, a non-trivial coupling between the polarization and the magnetization. So we can couple an electric field through the polarization, and we've designed in this strong coupling here. We can control magnetism. And yeah, okay, keeping track of time here. The first thing one has to realize is ferromagnetic insulators are fairly rare. You can count them on maybe one hand. And the fact that we want it to also be ferroelectric, and that we want to be able to tune from an anti-ferromagnetic paraelectric material into this phase is quite challenging. Right, so we have to come up with some mechanism, blah, 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 tuning mechanism, identify realization, fine. This is going to be example 1. I'll try to get to, yeah, I have time. So I'll get to at least example 2, maybe 3. Example 1, our starting point is what's our model? And so now I'm imagining that I have some Hamiltonian Hamiltonian, it looks like this, except my spins are fairly large, so this is going to be just imagine some classical Heisenberg Hamiltonian. What I'm going to do is to come up with a way to manipulate and control a structural distortion that controls the sign of the dominant interaction. We can control that sign, we can control whether or not the spins want to align parallel or anti-parallel. We control this ferromagnetic or anti-ferromagnetic to ferroelectric transition. And there's one thing I need to give you in terms of background, just one slide on ferroelectricity and a way of tuning ferroelectricity, or sort of a toy model of how these structural ferroelectrics come about is that there is an instability, a polar instability. Imagine you have your force constants at zone center, Q equals 0. There's an instability of your force constant, a particular type of force constant, a polar force constant. The system loses rigidity to that motion. It freezes in the structural distortion associated with that force constant, and this is how we describe the onset of ferroelectricity in materials like barium titanate and other such things. This idea that there's a soft mode, a polar soft mode that freezes in and stabilizes ferroelectric phase. So you can imagine having sort of, if this is your cartoon of that force constant, this phonon happily vibrating in this nice paraelectric well. We've shown, and people have shown experimentally and theoretically, that we can apply large strains of material. So you can imagine growing something that is paraelectric, like strontium titanate, on various substrates, apply large in-plane strains by matching up the lattice constants here, and drive the system that is nominally paraelectric into a ferroelectric state. So strain controls the onset of this paraelectric to ferroelectric transition. So with that, realizing that the key role of this polar force constant, imagine your system now couples in a very generic way to an underlying spin system. And it couples sort of like this typical spin phoning type of coupling, that your bare force constant couples quadratically or biquadratically to this spin-spin correlation function. So we have the bare phonon frequency, and in a system with spins, we couple, and this is a very trivial interaction, couple according to the spin-spin correlation function. Imagine that we had a way of taking this bare phonon frequency to 0. Now, depending on the sign of this thing, let's just assume that this is positive. Now the force constant itself depends on the sign of the spin-spin correlation function. For anti-parallel spins, we get a minus sign, we have a nice stable phonon. If the spins were somehow aligned, this interaction is positive. This leads to an unstable force constant, and we have a situation like this. So taking a system that has a generic spin phonon coupling, tuning the ferroelectricity down near to the ferroelectric or paraelectric ferroelectric transition leads to a system where we have the anti-ferromagnetic paraelectric state competing with the ferromagnetic state. Not really too important. We found a material realization, europium titanate. This is europium 2+, titanium 4+. Titanium 4+ is D0. Europium 2+ has a half-filled F shell. It's very large spins. There's J7 halves. Blah, blah, blah. We worked out this nice epitaxial phase diagram from first principles. Not really too important. The point I want to make is, in fact, my colleague at Cornell, Darryl Schlom, has made this on various substrates, apply these large strains, blah, blah, blah. We make them beautiful films. Again, this is in the interest of time and not really the point. They made them, yes, and we were able to demonstrate that we can control the system. We can take it from its natural anti-ferromagnetic paraelectric state and drive it with strain into this ferromagnetic ferroelectric state. That's great. This sort of model seems to be working. Unfortunately, technology plays some tricks with us sometimes in that we only have commercially available substrates that take us here, slightly to the left, which is again in the anti-ferromagnetic paraelectric phase, and all the way deep into the ferromagnetic ferroelectric phase. So we don't have substrates, we don't have the right strain state in order to get us into this region where we have these competing phases. But they've been working the last couple of years of working this out, and stay tuned. But the point is, this is the first time that we started with this model and came up with this way of manipulating the interactions to create phase diagrams that look like this. And so far, every experiment has been consistent with such a picture. In the last 5 minutes, since we want to end at leave 15 minutes for questions, let me just describe this second example where we start with, again, a classical spin model that looks something like this. That not only we take what we had before, where we had these symmetric interactions, and add some anti-symmetric interactions, like the desired Schiff-Riemann interaction. And an example that I'll show you is we're building up this material such that we can manipulate the sign of this D parameter here. What is that? Well, we know that, just for in case this is completely foreign to you, symmetric exchange interactions, and again, that oxides are mostly linked to the case of this antiferromagnetic spins that look something like this. But when we turn on these relativistic effects, like desired Schiff-Riemann interaction, single line anisotropy, these things lead to a canting of these spins. So this is what is referred to as weak ferromagnetism. It's the origin of magnetization in things like rust. Interestingly enough, the sign of this DM interaction, we're disregarding the single line anisotropy for the purposes of making this illustration a little clearer. The sign of this interaction determines the direction of canting. So if you could come up with a way of controlling the sign of D, you could control the direction of the canting. So you can imagine starting in a configuration like this, switching D and switching the direction of the canting, and switching the direction of the net magnetization 180 degrees between two stable states. Controlling that with an electric field if the Zeiss-Maria interaction was proportional to the polarization. So if you're in a state like with P up and the D is say positive, it spins with can up. And if you switch the polarization, and if that somehow switched the DM interaction, you could switch the direction of the canting with an electric field. Anybody who is at all familiar with these will object, because D is an axial vector and B is a polar vector. So that seems to be a problem. Said another way, if we look at interactions between a spin hopping on a lattice and go through all of Moray's calculations, the DM interaction really comes about, or what really matters is the handedness of the bond between one spin, the oxygen, and the other spin. So you imagine this electron here hopping through this oxygen and hopping to the second spin, vice versa. The sign depends on whether it's bent like that or bent like this. These have two different handedness and have two different DM interactions. The sign is different, right? The problem is that a polar distortion of a perovskite would never change the bonds like this. So imagine how I have my spin, I have my perovskite, I have my spin on the B side of the perovskite, I'm interested in this interaction. A polar distortion would never change the bonds this way, it would never change the handedness. But a rotation will. In fact, rotations that we talked about before in these perovskites completely determine the sign. One particular rotation completely determines the sign of this interaction. If the rotation rotates, say, in a leftward sense, the sign is one way. If it rotates in the other sense, the sign is the other way. So it would seem that if somehow we couple the electric field to the rotation, we can control the rotation, we can control the sign of the DM interaction. Long story short, because I'm running out of time, in simple perovskites, that can't happen. There's a very simple symmetry argument to see that. Again, it's not important. I'm running out of time. So, as a first way of, as a first attempt to go beyond that simple statement that rotations can't couple to an electric field, I sat down and thought, well, I can't. So that little structural motif won't work. But a structural motif like this could work, right? Don't have one pathway, but I have two pathways, right? And I want this net interaction to be zero in the parallel phase. reasons. I want it to be an antiferromagnet. So if I can find a motif like this with an inversion center between the two spins, I know from very simple symmetry arguments that the net DM interaction has to be 0. If I remove that symmetry, that inversion center now, such that, for example, like a ferroelectric distortion would, I'd bias one of these pathways over the other, and I would bias one sign over the other, and the net DM interaction would change sign. And that's exactly what we found in this realization. Iron, titanium, O3, and this in the lithium iodide structure. This is not the ground state structure. Iron, titanium, O3 forms in what's known as ilmenite. We found that if you could make it in this lithium iodide structure, this indeed would occur. And several groups have subsequently found this.
Sorry, can you back up? What's the difference in this? This is not exactly a perovskite structure. No, I'm sorry.
Yeah, no. I know this is going back quickly. Sorry.
That's okay.
So as Alex will, I have to say this correctly in front of her. She will object. Lithium iodide structure is not a perovskite. But from a physicist's symmetry point of view, I can start with the simple, there's a group-subgroup relation between a simple 5-atom perovskite and the lithium iodide structure.
And there's a coherent transformation path between them as well.
Oh, okay.
She's done
Distortional path.
the best work in the world ever on the ilmenite lithium iodide transitions and phase diagrams of it. That's why
Be very careful.
I will almost cut this out and talk. But the point is, in a very simple way, B cycle, the magnetic ion and B cycle will work. The magnetic ion and the A cycle will work.
Got it. Okay.
That is the very simple way of thinking about it. The connectivity is different between, even though they have this in the cubic perovskite, they have the same local site symmetry. The connectivity is different, and that connectivity matters.
Yeah.
All right. Long story. Okay. So where do I want to end? Yeah. I like these guys. New guys. Ferroelectricity has been going on for a while, right? And you can ask this question. You ask, I think perhaps you could relate to this in the discussions. I came in towards the end of the discussion this morning about reinventing IPAM or what have you. Is there anything new to invent, right? And in my mind, this is what I set out a few years ago to think about in the context of ferroelectricity, particularly because of this question of that I'm really annoyed that rotations can't couple to an electric field. In the last example, which I'm not going to go through, we figured out how to do that. That's all I'm going to say. And we can now directly couple to an electric field to the rotation, which controls this sign itself. It has to do with layering of various compounds, or layering of perovskites and interfaces of effects and blah, 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 blah. Right. Right. And so rotations have been known to be beautiful, right? Structure has been known. So here, since I'll end here, instead of going on, let me change the context of this a little bit. Structure has been known forever, right? We know the structure controls properties. We know it's quite beautiful. And what I've been asking myself, and what really the point of this whole talk is, can we do something functional with it? Can we use structure to create new, and can we control that structure to create new and interesting phenomena and functionalities? And whatever. I can see all my jokes. I can save them for next time. Great. Collaborators, all the experiments that you've seen, I have to just give this plug. Darryl Schlum at Cornell is a phenomenal person to work with in making materials. James Raminelli and Nicole Benedict have also collaborated a lot with. And the people who did most of this work, this is my student Andrew right here. and actually Nicole and myself, and James. All right, so with that, let me end, and we still have 10 minutes for questions.
Alex has a question.
Floor is open to questions. Alex?
Yeah. So, you know, many of the sort of, ordinary ways of looking at these problems is to say, let's imagine the structure and then let's do the highest level quantum calculation we can and get the energy of the structure. And here, of course, is where nature bites you, and then most of the materials we're dealing with have very small energy differences and they're limited resolution of calculation and sometimes of experiment. If I understand your approach, you never put actual energies on things, you're just making real symmetry arguments. This is the sort of interactions I need to get that particular set of properties, and then try to, but what I don't see, and I like that because it gets away from the bind of small energy differences, what I don't see is how you then, except in very special cases, say, okay, these are the atoms that have those interactions.
Yeah. That's a great summary and very insightful. And I wish I could have said it that nicely. That's actually correct. And I think in the first part of your statement, so the statement you made is absolutely correct. And that's what guides me, and that's how we get to what really needs to be in this material for it to be a realization. And that's why I consider these design rules. These are the things that are robust. These are the things that aren't going to matter which flavor of DFT you use, or how well you handle correlations in the problem, blah, blah, blah. All of these things that we have really no control over and no understanding of. That being said, where do I go with that? Even though I haven't really, and I try not to actually talk about it in my talks, discuss, oh, this is what we did, this is the energies we found, blah, blah, blah. In the cases that we've found so far, or that I discussed, sorry, these were those examples where we got really lucky in terms of finding, we built these structural motifs, we looked through the literature to find out what types of materials really these need to be. We found them, and lo and behold, in one case, Darryl was able to make a thin film and strain the heck out of it. In other cases, people like you have showed us how to use high pressure to stabilize these things in different structures. What I haven't talked about, and this is really the work in the rotations, is that right now I have no good example that I think is readily accessible, can be made tomorrow in somebody's lab, of a material where the rotations couple naturally to an electric field. We have lots of calculations on structures that we think could be, but I don't think any of them could be made. But from those and from the energetics that we're learning, we've incorporated all of that information into and refining these rules to help us better find that right material. So the short, that's may or may not answer your question, but fundamentally I believe that materials, just finding that actual material in the lab is so much better done by the person in the lab making that material. And that the theorist really, if they do their job right, really gets that experimentalist in all their chemical intuition, focusing them really in the direction of where to head and where to go. So I am not, yeah, so with that, I think I'll.
So you're proposing that we be motivational theorists.
Yeah, why not?
I think you're right. I'm listening to your talk, and I'm summoning up Bert Matthias, who was the great materials scientist for the middle part of the last century, focused initially on ferroelectrics, went off to superconductivity, and of course has left us as these major heritage people like Zach Fisk, who's like Nicole Canfield, etc. There you are.
Sorry, finish your point, sorry.
Yeah. Barrett would have been fascinated by the structure rotation things you said. He would, on the other hand, not have come to your talk if he thought it had anything to do with Hamiltonian.
That's right. So, yeah, this is what I love. I used to end my talks like this, but, you know, you always have to rewrite your jokes. But since maybe it's been so long since I said it, let me end here, since you did a nice segue to this. These were his rules for discovering new for new superconductors. Symmetry is the best, peaks and density states are good, stay away from oxygen, stay away from magnetism, stay away from insulators, stay away from theorists. You know, it's questionable 1 through 5, so maybe 6 is...
Actually, no calculation how the basic idea of BCS, the electron near the Fermi surface, development and attractive interaction, how that could explain Matthias's rules, because Matthias was a good friend, and I paid a lot of attention to what he said. And he gave a party for me.
Very much from your party.
Other questions, comments?
Alex has.
Let me
Alex,
try
go.
one more, and that is that lately there are lots of even more complex perovskite structures, things where you fool around with gas and you have ordered oxygen and nitrogen and when you're disordered, or you start putting in, the ones that really fascinating ways, you start putting in large complex ions, you know, or that.
Dan Jacobson's and things.
Things like that. Does that give you additional variables for your game?
Yes.
Yes.
And I could talk for a few more hours on Rosen Popper's, Dan Jacobson's, and how we can use. So one of the ways of creating these functional rotations is by layering A-site cations in simple perovskite. Essentially, what you're doing is trying to break this conductivity without really breaking it. So why don't we just go to systems where we really break the conductivity by shoving in large atoms? So imagine having a two-dimensional layer of a perovskite and shoving a large atom and another two-dimensional layer of a perovskite or something. These things naturally form, as you know, one structure is known as the Dion-Jacobson, others are known as Rosen Poppers. The group break themselves was N equals 1 Rosen Popper. The N equals 2 Rosen Poppers actually can be made ferroelectric using this technique. We can do layering of things, and yeah, I think that what I've shown and what I've talked about today from the structural, from the solid state chemist point of view is sort of the baby step. And we've been thinking about more interesting ways of doing this from the solid state chemistry perspective. I love to tell you about those.
I have a question. Sure. How many anti-ferroelectrics are known?
That is easier said than, okay. So the question is how many anti-ferroelectrics are known? And one has to, Jim Scott's not here, so I can, I would say 0. I think that's the simplest answer. There's the caveats and more discussion, but I think from a starting point, if we start with 0, I think I won't be too far off.
Why?
It's a great question.
What does it even mean?
So what does an anti-ferroelectric mean is even a better question. Because this whole idea that the simple Cattell model of an anti-ferroelectric is I have a small dipole in in this unit cell, and another dipole pointing in the opposite direction in this unit cell, and they're all the same, right? One up, one down, one up, one down. The whole notion that we have localized dipoles in an extended system doesn't exist, right? And very phase theory polarization just taught us that. So the whole notion of what really is an antiferroelectric is kind of complicated and not, I don't think, well defined. People are trying. Karen Ray has done a really good job recently of trying to define what we mean by one.
So we should go back to defining the can't create it, I don't understand.
That's about right, yeah.
Tom,
So that question actually more detailed. So you have this parameter J and a G in the model. Is this something you can calculate, or can you give us some idea of the relative strength? Because I would think that that's important.
Sure, no, we can calculate those and we've done
So how do they compare the relative strengths?
about a tenth or so in one case. Usually they're about, D's are always about a tenth or 100 smaller.
Yeah, I think they're kind of small, right?
They're kind of small, right?
So that it's very small, and you won't get a lot of this canceling and stuff that happens.
So I didn't talk about any numbers here.
Yeah,
But
that's the thing.
the sort of numbers that we're seeing are perhaps canting, net canting in some of these systems, largest about 0.1 per megaton. About largest, usually about half that. And that is what has in these ilmenite, iron titanium 3 and compounds like that in this lithium ionic structure. That's the sort of moments they were calculated and then actually measured. These things shouldn't work out well, but these are small. But right now we're still trying to figure out how to couple these things. And small moment, switching 180 degrees versus not having any examples it's measurable. That's the main thing, the measurable. And yeah. Cheers.
Marvelous talk, very inspiring. But one of the problems I have with your talking about my colleagues at breakfast is that they focus an inordinate amount of effort on systems with no electrons, insulators.
Yes.
And these are wonderful for control devices. But what are the prospects for adapting this general approach to the systems which are conducting?
Great question.
why don't you repeat it so the audience can hear it?
Certainly. There are no electrons in my system, and people love electrons. More seriously, the systems that I'm working on are band insulators or Mott insulators. What are the prospects for taking some of these ideas of control structure and moving them into regimes where the electrons are, the correlation among electrons are really the problem. And so sometime this week, the trustees will vote on my tenure case. And after that, I can move from problems that I know a lot about to problems that I know very little about. To help that, in fact, Munah Kim and I recently hired our first joint postdoc. And you know Munah, so she likes electrons. We're moving in that direction. This is why I'm happy unless I don't understand, and I don't understand anything about that. What a lot of the physics that we're talking about, and I want to see how well we can control those types of interactions of the structure.
We should have a go, I think, and then we'll go for a break, at doing an ICAM workshop connecting all the things you've been saying to the electron control systems, and we have many examples from heavy electrons, the group rates, etc. Things that move just like that, with superconductivity emerging as a maximum right at the border between antiferromagnetic and itinerant behavior.
This is why I'm here. This is what I want to learn more about. I want to make more
I think
context.
trying to bring those two communities together would make for
That's great.
Thank you.